Something that's always bothered me about speakers is this. If I place a microphone directly in front of a speaker, I get this nice clean tone. But if I move just a few inches to the left or the right, the sound disappears. And it's not just a mic, the sound I was just listening to is gone as well. The same thing happens when I move forwards, backwards, up or down. I'll get loud spots and quiet spots, all of which vary with frequency and location. It always makes me wonder if we're actually hearing the sound the way it was recorded at all. So I'm going to film the sound waves and see what I can do to get rid of all the highs and lows. To see sound, I'm using my DIY CAT scanner. But first I need to scale everything down, including the sound waves, so they fit inside the 8-inch scan area. It turns out that Lego is really good material acoustically to get a 40:1 scaling of the real world. For the sound source, this cat repellent speaker emits a 20 kHz tone, so scaling at 40:1 gives me a 500 Hz wave, which puts us right in the middle of the vocal pronunciation range. But I have a bit of a problem. The speaker doesn't scale down. Next to a normal Lego man, which is a 40:1 scaling of a human, it looks gigantic. But then I remembered my favourite movie, Back to the Future. Specifically the scene where Marty gets blown across the room by Doc Brown's giant speaker. Now if I bring in my Lego friend Marty, it gives me a perfect 40:1 scaling of a real human standing in front of Doc Brown's giant speaker. And now that's all grounded in reality, we'll be able to see what sound waves look like relative to a human. For our first test, I placed Marty standing on a wall and mounted the speaker over his head. The first few cycles of the sound wave, you can see that the waves emerge from the speaker and the ripples of pressure flow forward like waves in a pond. But look what happens when the waves hit a wall. The sound particle velocity is forced to zero. And the air particles can't go forward anymore, so they bounce off the walls and collide with the incoming wave. And this causes a fixed pattern of pulsating high and low pressure regions that sort of expand sideways. Because the pressure at the wall is high, there's a big difference between the middle and the ends of the wave, which forces the air to squeeze out the side. In between the ripples are the nodes and antinodes, and these are the grey areas where there's no sound at all. So these are the quiet spots I measured with my microphone earlier. The standing wave locks these into fixed locations relative to the wall. Now the top and bottom of my Lego room are open to the air, and I wanted to see what happens in a closed room with ceilings and floors. But I also needed light to travel through the room, hit the mirror and back out again. So I needed a piece of very flat glass, so that the glass doesn't bend and distort the flashes of light. Now if you use a mobile phone and angle a piece of glass, you can usually see ripples in the reflection. So after testing coffee tables and fridge shelves for optical flatness, I eventually found a reasonably flat piece of glass salvaged from this old mini oven, and voila, I had my clothes box. And looking at the room modes, I can see the patterns a lot brighter, as the sound is reflected from all 6 surfaces instead of 4. So how do we get rid of these modes? Ideally I want my speaker to radiate like ripples on a pond, which always move forward. I need to reduce the reflections. One method is to use sound absorbent material to slow the particle velocity. So first I tried some carpet on the walls. Then I tried some Lego slats to diffuse the sound. Then I tried some acoustic foam, which did a nice job, there was hardly any reflections. And then I tried some Rockwool, which also did quite a nice job. But what if the walls aren't flat? I wanted to see what would happen if I swapped the straight Lego walls for a curved one. First I made a curved wall with some plastic sheeting. Look at what happens to the sound waves. It acts a bit like a satellite dish. So instead of bouncing the sound straight back, it focuses them to a single point in front of Marty. If you sit exactly there, the sound will sound really boomy. And this is why vaulted ceilings are not a good idea acoustically. While having my morning coffee, I spotted the ideal thing to create a convex reflector. And a quick bit of salvage work, but it didn't work too well. The top was a bit too flat. So I added a 3D printed cone for my last video, and that did the job. Hardly any reflections. Now with a 40:1 scaling, this is basically the nose cone of an airplane. Not the most practical thing to put behind your couch. But what about the corners of the room? You often see people shoving massive bass traps into the corners, and I wanted to figure out why. When sound hits a flat wall, it bounces back, the acoustic pressure doubles, so that's a 6 dB increase. But in a corner you have 2 surfaces, which gives a 12 dB increase, and up in the top corner where the 2 walls meet the ceiling, you have 3 surfaces, and the pressure increased by 18 dB. but you don't get a pressure increase for nothing. With more surfaces, the region of the pressure increase becomes much more confined. Most of these sound cancellation techniques rely on friction to slow down the air particle velocity, but another class of techniques is to use a resonator. Now these use a tube or cavity which creates an equal and opposite wave, basically cancelling out the incoming wave across a small region. To see how this works, I built a wall out of Lego Technic bricks, which are full of these tiny tubes. But I had a bit of a problem. My speaker works best at exactly 20 kHz, and the Lego tubes were just a bit too deep to resonate at that frequency, so the sound bounces off a bit like a flat wall. So I couldn't change the speaker frequency, I had to change the depth of the Lego holes. So I placed the Lego wall into a shallow tray of water, a bit like blowing across a bottle of water. You can change the tone of the sound by varying the depth of the water. So I very slowly added water, and you can see the difference in the room patterns, but still not perfect. Not as good as Rockwool. Famous last words, maybe I can make it work with a bit more fiddling about. Now, a really fancy way to cancel reflections is to use another speaker to cancel the reflected waves, and this is called Active Cancellation. It sounds pretty cool. What's more, you can turn the second speaker into a microphone by connecting the input to an amplifier across its terminals. Now I can literally see the electrical signals as the sound waves from the first speaker hit the second speaker. Ideally, I'd like to invert this signal, then amplify it, which would then cancel the reflected waves. So without any thought, I connected the second speaker to a third speaker via an amplifier, thinking it would cancel the reflected waves. But this turned out to be a bad idea. It created this huge feedback loop which nearly deafened me, and that's no joking. So using a microphone and speaker to automatically cancel a room mode sounds great in theory, but it's really tricky to stabilize due to feedback. So then I just opted for the plain old manual method of guessing the phase and volume of the reflected wave and generating a second wave manually. And the results were a bit mixed. You can see it working very well in specific spots, but it's quite tricky to control. If you move an inch or tweak the phase a tiny bit, you can accidentally make the room sound a whole lot worse. Acoustics isn't black magic, and once you can see what's happening, it makes a whole lot more sense. If you want to build your own CAT scanner rig, click on the link that's here. And thanks for watching, have fun, and I'll see you next time.